Dear student, let us see today how to draw shear force and bending moment diagram for a simply supported beam having overhang and UDL plus a concentrated load. For that, we will consider one example. A simply supported beam ABC is supported at A and B 4 meter apart. BC is overhang of 1 meter. It carries a UDL of 12 kilonewton per meter over entire length and a point load of 8 kilonewton at free end C. Draw shear force and bending moment diagram. Now let us draw this beam AB 4 meter apart. BC is overhang 1 meter loaded with 12 kilonewton per meter over entire length and 8 kilonewton point load at C. Now to start with, let us find the reactions of the beam. So for reactions, let us apply the three basic conditions of equilibrium. Sigma Fx is equal to 0. This condition is already satisfied as there is no horizontal force. So sum is already 0. Sigma Fy equal to 0. For that, I am using the sign convention, upward force positive, downward force negative. Now to start with Ra, which is upward, so positive, minus the intensity of UDL is 12 kilonewton per meter and it is spread over a length of 5 meter. So 12 into 5 is the downward load plus Rb, upward reaction at B, minus 8 kilonewton, that is the point load at free end C. This must be equal to 0. So simplifying this, Ra plus Rb is equal to 60 plus 8, that is 68 kilonewton. So from second condition of equilibrium, we got this equation, that is Ra plus Rb equal to 68. So whatever load is coming on the beam will be taken by the support A and B, that is Ra and Rb. They will share 68 kilonewton. Now applying third condition of equilibrium, sigma m is equal to 0. For that, I will assume all clockwise moment positive, all anti-clockwise moment negative. Now, let us take moment about say B. So, taking moment about B. Now, to calculate the distance of UDL from B, what I am going to do is, I will draw a separate sketch here below this beam. And as UDL is for a length of 5 meter from A, for calculation purpose, it is assumed to be acting at the center of this A to C, that is 5 meter length. For calculation purpose only, the total load is 12 into 5, that is 60 kilonewton, is assumed to be acting at a distance 2.5 meter, that is half of 5 meter. See, the UDL length is 5 meter and it is assumed to be acting at the center of 5 meter, that is 2.5 meter from A, 2.5 meter from C, and therefore from B it is 1.5 meter. I will repeat, the center of 5 meter, that is from A 2.5 meter, from C it is 2.5 meter, and from B it is 1.5 2.5 meter. See, this is the center. From C it is 2.5 meter. So we will consider this distance for calculation purpose. Now, as I am taking moment about B, I will consider all the distances up to B and clockwise movement positive, anti-clockwise movement negative. So RA into 4. This is clockwise movement, so I will consider it as positive. Minus 12 into 5, that is the total UDL, which is acting at a distance 1.5 meter from B, plus RB into 0. Actually, though, there is no need to write RB into 0 as we are taking moment about B. RB is passing through B, so perpendicular distance is 0, plus 8 into 1. This is clockwise moment of that 8 kilonewton point load about B. This must be equal to 0. So 4RA minus 90 plus 8 is equal to 0. So 4RA is equal to 82. So RA equal to 82 divided by 4, that is 20.5 kilonewton. R equal to 20.5 kilonewton. Okay. Now, taking moment about A. Taking moment about A. Again, all clockwise moment positive, all anti-clockwise moment negative. RA into 0, no need to write, plus 12 into 5 into 2.5. See, the total UDL is acting at a distance 2.5 meter from A. So 12 into 5 into 2.5 clockwise movement. So positive, minus RB into 4 plus 8 into 5. 8 into 5 is a clockwise movement. See the distance from A of the load 8 kilonewton, it is 5. So 8 into 5, this must be equal to 0. So this is 12 into 5. Let us calculate 12 into 5 into 2.5. That is 150. So 150 minus 4RB plus 40 is equal to 0. So RB, 4RB is equal to 190, and therefore RB equal to 190 divided by 4. 190 divided by 4, we get 47.5. 47.5 kilonewton. So we got RA 20.5, RB 47.5. So let us check whether the total is equal to according to the equation 1 or not. So RA we got 20.5 kilonewton, RB we got 47.5 kilonewton. So total is 68 kilonewton, which is according to equation number 1. So whatever calculations are done are correct. Now let us draw the shear force diagram directly because we got RA and RB. So for that I am drawing first the baseline. Then at A there is an upward reaction of 20.5. So I will take some suitable scale or proportionate diagram I will draw. This is 20.5 RA. Then from A to B for a length of 4 meter there is a gradual drop of 12 kilonewton per meter. So 20.5 is the reaction at A, 20.5 minus 12 into 4, that is 48. So I got 27.5 minus. So at B there is shear force 27.5. I will repeat, at A we are plus 20.5, then the force due to load of 12 kilonewton per meter for a length of 4 meter there is a drop of 48 kilonewton gradual. It is not a concentrated load, it is a UDL, so drop is gradual. So from A to B there is a total drop of 48 kilonewton. So 20.5 minus 48, that is minus 27.5. Let us join these 2 points, 20.5 and 27.5 minus at B. Okay, now at B there is a upward reaction of 47.5. So 27.5 is minus plus 47.5. So 27.5 is minus plus 47.5, that is I got here plus 20. So at B there is a upward reaction of 47.5. So here I got 20. I will repeat, minus 27.5 plus reaction at B 47.5, so plus 20. Then from B to C there is a gradual drop of 12 kilonewton because the intensity is 12 kilonewton per meter and the distance is only 1 meter. So I got here 8. How? 20 minus 12, so 8, and at C there is a sudden drop of 8 kilonewton as there is a point load at 8 kil at C, which is 8 kilonewton. Now above the baseline mark it positive and below the baseline mark is negative. Then shade the diagram like this. So this is our shear force diagram. The unit is kilonewton. Note down these 2 points where the shear force diagram crosses the baseline. This, these points are known as points of contra shear. Point of contra means opposite. Contra shear means where the shear force changes the sign from positive to negative or negative to positive. The specialty of point of contrast shear is that here we get maximum bending moment. Always below the point of contrast shear, we get maximum bending moment. Now, let us draw the bending moment diagram. For bending moment diagram, I am going to use this sign convention. Suppose this is a section. and clockwise movement on left hand side and anti-clockwise movement on the right hand side positive. Similarly, if this is a section, anti-clockwise movement on left hand side and clockwise movement on the right hand side negative. This is the sign convention. Follow the sign convention strictly. Now remember this point, as I told you, the point of contrast here. We must locate this point because here the bending moment is maximum. I will call this point as X, and suppose this point is say D. Now to locate this point, I will consider the shear force diagram between A and B. See, I am just drawing the shear force diagram between A and B here. At A it is 20.5 and at B it is 27.5. Just I am enlarging this diagram between A and B. This is A point 20.5. This is B point which is 27.5. This is B point. The distance between A and D, I am assuming is it as X. So the remaining distance between D and B, this distance between A and D, I am assuming it as X. Total A to B distance is 4 meter. So this will be 4 minus X. Now using similar triangle rule, X upon 20.5 is equal to 4 minus X upon 27.5. So simplifying this, 27.5 divided by 20.5 is equal to 4 minus X. So if you simplify this, you will get the value of X is equal to 1.71 meter. I will repeat using similar triangle principle. These are the two similar triangles. So x upon 20.5 must be equal to 4 minus x because A to B is total 4 meter. 4 minus x divided by 27.5. So x we get 1.71 meter. This is the important point because here the bending moment is maximum. Now I will calculate the maximum bending moment. So Bm max is equal to, I will consider the left hand side of this D point. This is our D point. This is RA, which is 20.5 kilonewton, and the UDL on the left side of D for a length of 1.71 meter is 12 kilonewton per meter. Now bending moment at D, which is maximum, which will be equal to, again considering the sign convention, RA into 1.71 because the distance up to D from A that we calculated just is 1.71. So RA into 1.71, this is clockwise on the left hand side, so positive. minus 12 into 1.71 into the distance of this UDL again at the center of the UDL length, that is 1.71 divided by 2. So substitute the value of RA 20.5 into 1.71 minus 6 into bracket 1.71 square. So if you calculate this, what we will get, the bending moment at D is 17.5 kilonewton meter. This is the bending moment maximum at D. So we got bending moment at D. Bending moment at A and C, 0. Bending moment at A, as it is a simple support, it is 0. Bending moment at C, which is free end, also 0. Now let us calculate bending moment at B. Here I will consider right hand side. On right hand side of B, there are two forces. One is concentrated load 8 into 1. 8 into 1. This is clockwise but on right hand side. So minus, according to our this sign convention, 8 into 1, that is minus. Then moment of that 1 meter UDL minus 12 into 1 into 1 by 2. The again center of 1 meter, that is 1 by 2. So minus 8 minus 6. So minus 14 kilonewton meter. We got moment at this important point. So let us draw the bending moment diagram. I will project these lines are A point. This is the projection of A point. This is the projection of D point. This is the projection of B point and projection of C point. Then I am going to draw the baseline. This is the baseline. Remember, bending moment at A is 0, at C it is 0, at B it is minus 14. So below the baseline, don't write minus because we are marking it below the baseline. And bending moment at D, which is maximum, that is 17.5 kilonewton meter positive. Now, as there is a UDL, join all these points with a smooth curve. I am joining the point with smooth curve above the baseline, mark positive, below the baseline, mark negative. Let us do some shading work. Just remember, this is a parabola curve. In bending moment diagram, we get curve. Write down here BMD. Unit is kilonewton meter. Right here for the shear force diagram, its name SFD. Unit is kilonewton. Now note down this point. This point where the bending moment crosses the baseline is known as point of contraflexure. Remember, flexure means bending. Point of contra means opposite, where the bending moment changes sign from positive to negative. is point of contraflexure. Now our job is to locate this point of contraflexure. Let us consider the distance of point of contraflexure is at x0. Suppose this distance is x0 from A. So I am drawing the sketch right left hand side of x0. See, this is x0, left hand side of point of contraflexure. This is Ra equal to 20.5 kilonewton, and the UDL is there. This is point of contraflexure. Let us call this point is say E. So this is E point. This is 12 kilonewton per meter UDL, which is given. Now, if I write equation bending moment at E, which is equal to 0. See, here the bending moment diagram crosses the baseline. So bending moment at this point E, which is at point of contraflexure, it is 0. So bending moment at E is 0, which is equal to Ra into x0, Ra into x0 minus 12 into x0 into x0 divided by 2. So 0 is equal to Ra is 20.5 into x0 minus 6x0 square, 12 by 2 is 6, x0 into x0, x0 square. So simplifying this, x0 square is equal to 20.5 x0, cancelling x 1 x0 from this side, left side and right side. What I will get, 6x0 is equal to 20.5. So x0 is equal to 20.5 divided by 6. So 20.5 divided by 6, 20.5 divided by 6, I get 3.42. So this x0 I got 3.42 meter from A. So point of contraflexure is at a distance 3.42 meter from A. So this completes our shear force diagram and bending moment diagram. Please note down point of contra shear and point of contraflexure. Point of contra shear is the point where shear force changes its sign from positive to negative or negative to positive, and point of contraflexure is a point where bending moment changes its sign from positive to negative or negative to positive. One thing I must tell you, that is there are two points of contrast here. So as the below the point of contrast here the bending moment is maximum, then how there are 2 points having maximum bending moment? This is the question. The answer is at this point, at this first point, the bending moment is maximum, but it is positive maximum at this point. It is positive maximum. Below the point D, we get positive maximum bending moment, and below the point B, at point B, where there is another point of contrast here, we get maximum negative, that is minus 14 is maximum, and here plus 17.5 maximum. So the sentence is correct, that is at point of contrast here we get maximum bending moment. There are 2 points of contrast here in the given problem. At one point of contrast here we get maximum positive bending moment, and at another point of contrast here we get maximum negative bending moment. So this is the shear force, and bending moment diagram. This is the solution of the given problem. Thank you.